Dr. David Rapisarda. Dr. David Rapisarda is actually, well, you certainly know, you hear that ITER, IFMIPDONES demo, there are key components. Those key components are the test blanket modules, TBM. So this guy, Dr. David Rapisarda, is the head of the unit of TBM in the Nuclear Research Center of Spain, but he is also the leader of one of the TBM, the test blanket module in European program. So he's perfectly the key person to talk to all of you about how a test blanket module with so many responsibilities to extract the heat, to breathe the tritium, to be the first wall in many aspects for neutrons from the point of view of safety, are designed for a demo reactor, for a real reactor in the European Union. So I again want to thank you, David, for your ability to be here with all of us. And please, the floor is yours.
Okay, thanks so much. Thanks to you, and thanks to the organizers for inviting me to give this presentation. Thanks also to other presenters for being here after a very long day. So today I'm going to talk you about the European program on breathing blankets, which is a key component, as you will see in my slides, for a future demo reactor. But I have the feeling that this talk is not only interesting for people interested in magnetic fusion, because of course you will find some synergies, a lot of synergies with blankets for inertial fusion. So you will see a lot of similarity. I will focus on magnetic fusion because this is my field of expertise, of course. But a lot of things that I'm going to tell you can also be applied to inertial fusion. So these are the contents of my talk. Firstly, I will focus on the breathing blankets and the TBM program. And after that, I will focus on the European breathing blankets that we are developing during the last years. And of course, I will make some slides for the Spanish program on the dual coolant lead lithium, which is one of the most interesting blankets for the long term. And finally, I'm not only to talk about advantages of the breathing blanket, but also some technological issues that at the end are the root for our R&D program. So my intention today is not to give you a quite precise presentation on equations and so on, but I want you to go home with a clear idea of what is a breathing blanket, the main functions of the breathing blanket, and what is the difference between the different blankets that we are considering. So starting with the fission reaction, because I would like to fix some basic ideas. The fission reaction is driven by deuterium and tritium, which are two isotopes of hydrogen. And deuterium and tritium are used because this is the most attractive reaction because it has the highest cross-section at low energies. As you can see, okay, the pointer doesn't work, but you can see in this figure. So, and what is quite important of this reaction? Deuterium is commonly found in nature as a percentage of hydrogen in water. So we have a lot of deuterium in Earth. We have we have this fuel for more than 10 to the 10 years. So no problem with that. But we have an important problem with tritium. Tritium is mainly an anthropogenic element. This means that it needs to be fabricated. We cannot find tritium naturally in the Earth. We only have some small amounts of tritium in the high layers of the atmosphere by the action of cosmic rays. So, and the few production of tritium in the world comes from fission reactors and spallation sources. So, for that reason, tritium has to be regenerated in the reactor. This is a key point that you have to kept in mind. So, but how to obtain tritune? In fission, what we do is to produce tritune through lithium reactions with the neutrons coming from the fission reaction. These neutrons are of 14 megaelectron volts, so a very high energy, and this is also quite important. And why lithium? Because lithium, firstly, we have a lot of resources of lithium around the world, both in the continents and the oceans. And secondly, because lithium has two isotopes with a good cross-section for producing tritune. This is the main point. And these two isotopes are lithium-7 and lithium-6, and naturally, about the 90% of the lithium is found is lithium-7. Lithium-7 work, as you can see in the picture, mainly at high energies. Is the green curve in this picture. So lithium-7 interacts with the fission neutrons without any problem and produce a tritune and an alpha particle and an additional neutron. And lithium-6 also produces tritune, and what is interesting here is that the cross-section of lithium-6 is really large. It's large at low energies, so this is good. But the problem, as I mentioned, that naturally we found in lithium-7. So we need some enrichment in lithium-6 of this fuel. Okay, so summarizing, we have the fuel that we use in fusion is deuterium, tritune, and lithium. We need a small amount of tritune to start the operation of the reactor, and after that we operate with lithium. Okay, we have deuterium plus tritune, we generate neutrons, and these neutrons impact, I will explain where, and we will produce tritune again. So, the breathing blanket. In this slide, okay, I will try to, no tenemos nada por ahí, ¿no? Okay, it doesn't matter. Okay, this is a fission reactor. Okay, this is how it looks like. In the center of the reactor, we have the plasma, the deuterium and the tritune, and immediately surrounding the plasma, we have the breathing blanket. This is the first component that the neutrons see, and this is quite important. So the neutrons produced inside the vacuum vessel, which is this green part of the reactor, these neutrons goes directly to this part, which is the blanket. This is the breathing blanket. And after that, we have also some magnets to produce the magnetic field and so on. Tomorrow in the talk by Joaquin Sanchez, you will obtain more information about that. But this is important. The blanket is the component which is placed surrounding the plasma. So the main missions of the blanket. The first one, and quite important, is to extract the power of fusion in order to produce electricity. This is the most important. And secondly, because we have this lack of tritium in the world, the second important objective is to produce tritium via lithium reactions with the neutrons. These are the two main functions. And we have an additional function, which is the shielding of all the components behind the blanket. In this case, the vacuum vessel and the TF coils, the toroidal field coils. So, since we have to warrant the tritium self-sufficiency, this is, remember this word, is the self-sufficiency. We want to be self-sufficient with the fusion reactions. The blanket must contain the breathing material, in this case, the lithium. Okay? So, and these three functions makes the blanket the most complex component in the energy field. Okay? There are other components in other energy fields that with these functions and so on, but this is the only component that has the three functions in the same component, and this is quite important. Okay, the breathing blanket and the TVR. The TVR is a number that we use to measure this tritium self-sufficiency. The TVR is the tritium breathing ratio and is the number of tritium, the amount of tritium that we produce inside the blanket versus the neutrons produced in the fusion reaction. And this is quite important number. It's a really important number, and you will understand easily why. I said that the deuterium-tritium reaction only produces one neutron, and this neutron has to directly impact the lithium blanket. Okay? And in this reaction, we only produce one tritium. So we have one neutron, one tritium. this means that if we lose some neutrons on the way, we never will reach the self-sufficiency of the reactor. This is quite important. And we are going to lose neutrons. Why? Because the first thing is that, as you can see in this picture, the plasma is not complete surrounded by blankets. We have some other, this is the blanket, okay, and we have other components such as the diverter, or we have holes to install the heating systems or the diagnostics and so on. So at the end, we only have 80% of the surface of the plasma covered by blankets, and this means that we never will reach the self-sufficiency. Second point, the structural materials also absorb neutrons. These neutrons will go directly to the steel, and the steel will heat up, and we lose these neutrons. And the third point is that we have neutrons with high energy, and these neutrons can pass through the blanket without any interaction with the lithium. So at the end, we never will reach the self-sufficiency only with the lithium. And for that reason, we need in the blanket what we call neutron multipliers, which simply is an element which can absorb neutrons and produce additional neutrons, okay? And in our case, we use lead and beryllium. Okay, in this slide, I just wanted to show a schematic of the operation of the breeding blanket. It's quite simple, but I think that it can help to understand well the problem. Here we have the plasma with the deuterium and the tritium. We produce neutrons, and here we have the blanket, okay? In the blanket, we have lithium, which is the breeder, and we have some neutron multipliers. So with a fission reaction, we produce neutrons, which impact the blanket, producing heat and tritium, okay? And we have to extract the heat to produce electricity and the tritium for the self-sufficiency of the reactor. What happened with the tritium? We need a carrier to extract the tritium from the blanket and route this tritium to the tritium extraction system. The tritium extraction system is one of the most important subsystems in the reactor because we have to extract the tritium. This is quite important. So we have the carrier and we have the extraction system. And what happened with the heat? We also have to extract the heat, and for that we use a coolant. We have different kind of coolants. I will go with this later. And we have the coolant directly connected to a heat exchanger and to the primary heat transfer system. Okay? So at the end, what is important is that we need a blanket with two important subsystems, which are the tritium extraction system for the self-sufficiency and heat exchanger or the primary heat transfer system for production of electricity. Okay, during the last years, a number of concepts, of blanket concepts have been studied based on different breeding materials, neutron multipliers, and coolants, okay? And the first family of blanket concepts is based on solid breeder designs. In this case, we use lithium ceramics as breeder and beryllium as neutron multiplier. We use solid breeder materials in form of lithium oxides or lithium ceramics, and we'll also talk about the most accepted ones or more studied one. The first one is the lithium oxide, which is really interesting because it has the highest lithium content, but it has a quite important disadvantage, and is that it precipitates the formation of lithium hydroxide, and this means that at the end we are going to lose lithium and tritium, and we can't recover tritium easily. So for that reason, we go directly to lithium ceramics. And in the case of the lithium ceramics, we have studied two main ceramics, the lithium orthosilicate and the lithium metatitanate. They have different properties, but the most important difference is that the lithium orthosilicate has a higher lithium content, higher than the lithium metatitanate, and also a higher thermal expansion. For that reason, I will focus on that, and I will explain you later in a slide dedicated to this material. And as I mentioned, beryllium in the form of pebble bed is used as neutron multiplier. Why beryllium? Because it has a good neutron multiplication properties for high energy neutrons. I have not put here the cross section, but believe me, it has quite good properties. And quite important also, has low neutron damage. The pebble diameters are between 0.5 and 1 millimeter for the breeder and about 1 millimeter for the neutron multiplier. The second, I'm sorry, and okay. Among the different solid breeder designs, we can find a lot of concepts have been proposed, but these are the most common. The first one is the HEPV, which is a concept of pebble beds, but cooled with helium, okay? Helium-cooled pebble bed. The second is the water-cooled ceramic breeder, again, a concept of a solid breeder, but in this case, the coolant is water. The helium-cooled ceramic breeder is almost the same, but developed by another country. And the HCCR, which is the helium-cooled ceramic reflector, which is use a reflector to increase the number of neutrons. The second family of blankets is composed by liquid breeders. In this case, what we use is the eutectic alloy of lead lithium, which is a metallic alloy, where the lithium acts as breeder and the lead is the neutron multiplier. In this case, we have used, among the different eutectic compositions that this alloy can have, we have used this one, lead at 83% of lead and 17% of lithium, because it presents the lowest melting temperature of all the compositions. The melting temperature is 235 degrees, and this is easier to manage with the piping and so on of the system, and also to maintain between the limits of operation of the structural material, which in this case is Eurofer. And also the lead, because it's a good neutron multiplicator. It has a good cross-section for neutron multiplication. And what is important here is that small variations of the percentage of lithium affects important numbers in the blanket, such as the tritium breeding ratio. The tritium breeding ratio, remember the number of tritium that we produce in the blanket versus the number of neutrons, the tritium solubility, and also the melting point. So maintaining the properties of the alloy is quite important. This is the most important message. Okay, among the different liquid breeder designs that we have studied, we have the helium-cooled lithium lead, which is the tritium carrier. The tritium breeder is the lithium lead, and the coolant is helium. The water-cooled lithium lead, in this case we use water as coolant, and the dual coolant lithium lead. And I will talk on this blanket in future slides, in upcoming slides. The test blanket modules. Okay, as Angel explained in his talk, the mission of ITER is not to produce electricity and is not to breed the tritium. The mission of ITER is to have experiments to demonstrate the fusion reactions and so on, but we don't want to produce electricity. For that reason, in ITER, we will not have blankets. Instead of the blankets, we will have, you can see there in that picture, we will have shielding blocks, around 440 shielding blocks. And these blocks will be installed around the plasma. And only in certain positions, we will install TBMs, which are test blanket modules, which will be mock-ups of the blankets that we want for demo, adapted to ITER, okay? And in ITER, we will test 6 different blankets installed in 3 different positions. But the message is, in ITER, we will not have breeding blankets, we will have TBMs, which are mock-ups to test the breeding blankets, okay? The rest of the first wall is a shielding component. The main challenge for the TBM in ITER, the first one is to test the reduced activation steel, which is Eurofer, which has been never tested in nuclear industry and will be tested also in DONES. This is quite important, but in ITER we will have also some ideas of the behavior of the steel in a fission environment. To work under high operational temperatures between 300 and 500 degrees Celsius, they will operate in pulsed operation, We will test new manufacturing technologies, and we also test the functional materials, in this case the lead lithium and the pebbles. So the TVM will be a key component in ITER because they will help to identify the most promising technologies for demo. And what happened in Europe? In Europe, we will test 2 different TVMs, okay? And these 2 TVMs will try to cover all the technologies available in terms of coolant and breather. We will test coolant, we will test helium, and we will test water. And in terms of breather, we will test the pebble bed and the liquid metal. So the 2 TVMs that are being considered are the WCLL, the water-cooled lead lithium, and the HCPV, the helium-cooled pebble bed. So we cover all the technologies for the breathing blankets. Okay, now I will focus on the European program for the breathing blankets. So I will talk a little bit about demo, the high-level objectives of the European strategy, which consider demo as the only step between ITER and the fission power plant, are firstly to resolve all the remaining physics and technical issues foreseen in the plant. Secondly, to demonstrate the production of electricity. Of course, to demonstrate the self-sufficiency of the reactor to produce tritium, and to operate with adequate availability and reliability. Now, we have a new strategy which considers demo as a component test facility for the breathing blankets. This means that we will use demo to test the breathing blanket. And we also will test advanced technical solutions in parallel for the application for the fission power plant. The main requirements of the breathing blankets in demo. The first one, again, the tritium self-sufficiency. These are the 3 main functions of the blanket, okay? Second one, to extract the power to produce electricity. Third, the shielding ability. We also have to, we also must have an adequate structural integrity, both during operation and in accidental conditions. Considering the lifetime, we will have a first set of breathing blankets able to work up to 20 dPa. And after that, we will install a second set of breathing blanket to work at higher dPa, 50. Of course, another important requirement is the integration in the demo plant. For example, we only have this blue space dedicated for the blanket, so we have to design our blankets according to this limitation, also the piping in the plant, and so on. And of course, the concept must be intrinsically safe. In demo, we will install 2 different kinds of blankets. This is new from 2 years ago. And the first one is the driver blanket, and the second one is the advanced blanket. The driver blanket has to demonstrate the tritium self-sufficiency and the power extraction, while the advanced blanket is a concept which is potentially attractive for commercial reactors. So in demo, in the fission reactor, we will have a lot of blankets, and only a small part and a small fraction of all the blanket will be dedicated to the advanced blanket. Okay? For that reason, because both blankets will be installed in the same machine, they have to be developed at the same level of detail. This is quite important. Also quite important, the driver blanket will be directly connected to the primary heat transfer system. Okay? But the advanced blanket will use its own cooling loop. This means that the driver blanket, only the driver blanket will contribute to the production of electricity, because at the end, the advanced blanket can use a coolant which is completely different to the driver one, and we cannot merge this in the same primary heat transfer system. So this is a high-level decision. But the unique high-level requirement for the advanced blanket is that it has to produce tritium, and it has to contribute to the self-sufficiency of the reactor, because one of the missions of demo is to demonstrate the tritium self-sufficiency. That is, to produce tritium enough so we don't depend on external sources from the reactor. The first driver blanket that we are considering is the HCPV. You will see that we are considering two driver blankets, the HCPV and the Dcll, and this is because they are in line with the program of ITER, with the TVM. As I explained you that we want to cover in ITER all the technologies, water, helium, pebble bed, liquid metal. So the blankets that will be tested in demo are coherent with the TVM tested in ITER. So the driver blanket HCPV, helium-cooled pebble bed. In this case, in all the cases, the structural material is Eurofer, which is the reduced activation steel. In this case, the tritium breather is the lithium orthosilicate in form of pebble bed, and the neutron multiplier is beryllium. You can see in this picture that they are arranged in a form of a sandwich. We have a lot of beryllium, small slice of breather, and so on. The coolant is helium at 8 megapascals, and the inlet and outlet temperature of this coolant are 300 degrees Celsius and 500 degrees Celsius. And what is important here, and I'm going to the next slide, is this one. I go back to the schematics of the breathing blanket. We need a tritium extraction system and a heat exchanger. For the HCPV, this is quite important because how can we extract the tritium? Because we have the pebbles of lithium, the neutrons impact the pebbles, we produce tritium inside the pebbles, and we need to extract this tritium from the blanket. So for that, we use an additional loop of helium, which is used as a purge gas. Okay? It's a carrier, it's a gas which goes through all the pebbles and carries all the tritium to the tritium extraction system. And additionally, we have the second loop, or another loop of helium to extract the heat. Okay, and this is another scheme of the same, more complex. Okay, and this is the second. This is the second driver blanket. This is the Dcll. In this case, we have as breather the liquid metal, the lead lithium, and as coolant we have water. Okay, water at these conditions. I will explain right now. In this case, we use also Eurofer as a structural material. In this case, the neutron multiplier is the lead lithium itself. And for the coolant, and this is quite important, which is water, we use double-wall tubes. Why? Because we don't want that the lead lithium and the water interact. So we need a double wall to avoid, imagine if the first tube is broken, you can spill some water into the lead lithium. So we put two tubes, one inside the other, to avoid this problem. The coolant pressure is 15 megapascal, and the temperatures are slightly lower, are 285 degrees at the inlet and 325 at the outlet. In this case, the lead lithium, you can see here the blanket. Remember that this is the torus of the machine. This is the blanket. The lead lithium flows vertically, covering all these plates, okay, in this direction. And the water flows in, this is a cross-section in this part, okay, at this level. And in this cross-section, you can see the disposition of the different tubes with the water. The concentration close to this part, which is closer to the plasma, is because the neutrons impact more in this part, so there are more heat here, and we have to extract this heat, and for that reason we have more tubes. It's quite simple. Okay. Going back to this slide of the main subsystems, in this case we have the breather is lithium, the neutron multiplier is lead, the coolant is water. For the tritium extraction system, we have a dedicated dedicated loop of lead lithium. In this case, the lead lithium is the carrier because we produce the tritium in the lead lithium and goes directly to the tritium extraction system. And in this case, the coolant is the water and goes through this loop to the heat exchanger. Okay, this is more or less the basics of this blanket. Okay. And finally, we have one of the advanced blanket designs that we are studying, which is the dual coolant lithium lead. In this case, the structural material again is Eurofer. The tritium breather and carrier, again, as in the case of the Dcll, is the lead lithium. the neutron multiplier, the lead. But in this case, there's a quite important difference. I'm going to the next slide, and we'll go back to this one. In this case, the lead lithium acts also as coolant. We don't have any additional coolant. So this means that the neutrons deposit all the energy on the lead lithium, producing heat and producing tritium, and we route this lead lithium through the tritium extraction system, and after that, through the heat exchanger. So in this case, the lead lithium is the main coolant and the tritium carrier. And this is a difference, an important difference compared to the WCLL. But why dual coolant? Because we use an additional coolant for cooling the first wall. The first wall is one of the most important components of the blanket, which is the part is the first component that the neutrons and the plasma radiation see. So at the end is the component that receives the most important thermal loads, the most important radiation, and so on. So it's a quite important component. And for that reason, we use an additional coolant, which is helium, to cool this first wall. And for that reason is the dual coolant lithium lead. Okay. So the Spanish program, I think that I'm more or less on time. Okay, the Spanish program is the dual coolant lithium lead, and this is the reason I left this advanced blanket for the end. We have been working in the last years, during the last 10 years, in this interesting blanket, which started in Germany. After that, in US, there was a very interesting program on dual coolant lithium also, and in some way it came back to Europe in the last 5 years, and was developed here in CIEMAT, led by CIEMAT, and I will explain some characteristics of this blanket. As I mentioned, the dual coolant lithium lead uses the eutectic alloy of lead lithium as tritium breeder, neutron multiplier, and tritium carrier, these requirements. The coolant is lead lithium mainly, but also helium is used for cooling mainly the first wall, but also some parts of the structure. One important characteristic of the dual coolant lead lithium, the Dcll, is that the liquid metal flows at high velocity because we want to extract most of the reactor power. If we don't route the liquid metal at high velocity, it will heat up and heat up and heat up due to the neutron interaction, and we don't want that. So we have to flow the liquid metal at high velocity, and this has an additional consequence. The immediate consequence is that we have a liquid metal, we have a metal moving in a strong magnetic field produced by the coils, and we produce huge magnetohydrodynamic effects. Magnetohydrodynamic is a combination between the magnetic field and the hydraulic of the liquid metal. And to avoid, I will go in the part of technical issues, but to avoid this point, the Dcll uses a quite important component and a special component. It's a ceramic component called the flow channel insert. Okay. The Dcll is based on a multi-module segmentation architecture, which means that we have a number of modules like this, you can see here, attached to a common back supporting structure. Okay, we have several modules, and inside each of the modules, okay, I will explain later. Okay, as explained, in the Dcll, both coolants must contribute to the power balance, maximizing the ratio between the inlet and the outlet temperatures, but most of the power is extracted by the lead lithium, because this is interesting for the efficiency of the plant, because for pumping the lead lithium we need lower pumping requirements than for pumping helium, for instance. So this makes the Dcll probably one of the most interesting concepts for the long term for installing in a fusion reactor. The main advantages is that we have a wide design margin to the double cooling system. We can play a little bit with these two coolants. We have a low tritium inventory. We don't have any issue related to water because we cool with helium. Of course, I'm making a comparison with WCLL, but it can work for the presently available nuclear materials, and in particular for Eurofer, and it can be used for high temperatures, which at the end will mean that we will have a higher plant efficiency. And this is at the end, this is the key of the fusion reactors. Each of the modules is internally divided into different lead lithium circuits. Okay? The lead lithium enters through the lower part at 300 degrees Celsius. Here we have most of the gain due to the neutron interaction. We have nuclear heating here, okay? Makes this route and exits the module in this part at 550 degrees Celsius. And here you can see a breakdown of the blanket. This is maybe not so important, but the most important thing is that we have here different circuits of the liquid metal, and here what we call the first wall, which is composed of a plate of Eurofer covered by tungsten layer. Okay, what we do in CMAT is the CAD design of the Dcll, what we have adapted to the different demo layouts developed by Europe. We also calculate some neutronic responses, the most important figures such as the TBR, the nuclear heating, the damage in the components, and so on. Also, we perform thermal hydraulics calculations to obtain the temperature of the different components of the first wall, the temperature at the inlet and the outlet of the liquid metal. Also, we perform MHD activities, okay, mainly to estimate the pressure drop in the circuits. This is the immediate consequence of the MHD. We also perform structural behavior of the blankets, and of course integration activities such as the integration of heating systems, the piping layout, and so on. Okay, and this is in few words, this is the work that we are carried out here in CMAT, in Spain. And now I will talk you about some technological issues that are the drivers for the R&D program on breathing blankets. The first one is the fabrication, because we have to fabricate, and this is quite important, with nuclear standards, these complex structures. And this is common to all the blankets. Of course, we have to assure the tritium breathing. We have to minimize the tritium permeation. I have not talked about tritium permeation, but tritium can permeate through everywhere. So at the end, we will have the problem of tritium not only in the blanket, but also in the subsystems, in the tritium extraction system, in the heat exchanger, in the piping, and so on. So we have to avoid this tritium permeation or minimize. And we have to design and fabricate the first wall. We have to withstand about 1 megawatt per square meter, which is a lot. Some issues related to blankets that use the liquid metal. The first one is to avoid the chemical reactivity of the liquid metal with water and with air. Next, we have to control the impurities in the liquid metal. Also, another important issue is the corrosion of the structures due to the interaction with the lithium, and the MHD effects. And in particular, for the other driver blanket, which is the HCPV, we have some issues such as the fabrication and the general behavior of the pebble beds. Quite important, remember that the coolant in this case is just helium, only helium, and to pump helium is really is expensive in terms of electricity. It has some cost, so we have to to develop effective helium cooling schemes for these large internal structures. And of course, we have to design the circuit for minimizing the pumping power. And now, some technological issues related to the Dcll. Because as mentioned, the main problem of the main characteristic of the Dcll is the high velocity of the liquid metal. But this also is the main problem. Firstly, because this brings MHD effects, which can be mitigated through these flow channel inserts. I will show you now what is the flow channel insert. The corrosion also due to the velocity of the liquid metal, not only the velocity, but the combination between temperature and velocity of the liquid metal. Tritium permeation into the helium circuits, and the tritium extraction, quite important. Few slides about each of the topics. First one, magnetohydrodynamics, the interaction between the magnetic field and the movement of the liquid metal. The problem is that we have very intense magnetic field, around between 5 and 9 Tesla, depending on the place of the reactor, which is perpendicular to the flowing liquid metal. And in this case, this causes MHD effects, which at the end are pressure losses in the circuit. This is the main problem. And the solution that was found in the past 20 years ago to solve or to mitigate this problem is the introduction of insulating channel inserts. These flow channel inserts has these main requirements. The first one is to have a low electrical conductivity, to have low thermal conductivity, to accept high thermal stresses, and of course to present a good behavior under irradiation. We have different approaches for the design. You can see, maybe you cannot see quite well, but in green you have the liquid metal, in gray is the structure, and in white you have the flow channel insert, which separates the liquid metal from the steel. In this case, the ceramic acts as electrical and thermal insulator. We have another possibility, which is using 2 layers of flow channel insert. The outer layer, which is this one, okay, is composed by different layers, bounded ceramic plates to minimize the thermal stress, and the inner layer is for reduce the MHD pressure drop. What we are doing in CMAT is to design and fabricate these important components. We manufacture complex flow channel insert prototypes, as you can see here in these pictures. And we also characterize all these prototypes in terms of electrical conductivity, the properties of the mechanical properties, the compatibility with the liquid metal, that is corrosion, and the mechanical behavior. Okay. Corrosion. Another important point is the chemical compatibility between the liquid metal and the structures of the blankets. This is not a particular issue of the Dcll. This is an issue for all the concepts using the liquid metal. In this case, we need a low corrosion to have a safe and reliable operation. However, most of the experiments on corrosion have been performed without a magnetic field. And as you can see here is a small example, but what is important to say is that this data presents a very large scatter in the results. So we need additional experiments to confirm all the behavior of corrosion with the materials. So needs concerning the corrosion due to liquid metal. We need to study the mechanical properties in order to determine how serious this corrosion behavior acts on the steel. And of course, we need experimental tests on corrosion at relevant conditions. That means at high velocity and high magnetic fields. And of course, in CMAT, we are working on that. And one possibility to prevent corrosion, and this is one important part of the experimental program, is the development of coatings. And for coatings, we are investigating alumina and silicon carbide. Tritium permeation. Tritium permeation is another important issue for the blankets in order to control tritium leakage, because remember, tritium is radioactive and we don't want that permeates to the environment. And of course, to minimize the permeation to the helium coolant, also for tritium economy, because we want the self-sufficiency. So at the end, we have to maintain all the inventory of tritium well controlled. what we are thinking is to use the coatings for corrosion also as anti-permeation barriers, because at the end it's ceramics, and these ceramics can act also as anti-permeation. And for that reason, we are studying also the silicon carbide and the alumina coating. And finally, the last issue I wanted to mention is the Tritune extraction. Remember that our main objective is a fast and efficiency recovery of Tritune in all these forms from the eutectic lithium. And for that, we are investigating different techniques, the gas-liquid contactors, the permeation against vacuum, and so on. And in CMAT, we are also studying these properties in dedicated liquid metal loops. So, summarizing, and this is the end of my presentation, a critical component in future fission power plants is the breathing blanket, which has to assure the tritium self-sufficiency of the reactor, the power extraction to produce electricity, and is a primary shielding, is a component which is a primary shielding for the vacuum vessel and for the coils. The present breathing blanket designs are based on the use of liquid metals or lithium ceramics. And right now, demo is considered as a component test facility for the breathing blanket, and for that reason, we will have two kinds of blankets to test: the driver blanket, HCPV Dcll, or the advanced blanket that in some way could be the Dcll. And these driver concepts are the same concept that we are testing also in ITER as TVM, the HCPV and the Dcll. And Spain is leading the design of the, for me and for a lot of scientists, the most attractive breathing blanket for the long term, the most attractive blanket to be installed in a future fission reactor. And of course, we are still working in some specific fields for R&D, corrosion, Tritune recovery, coatings, and so on, for the development of the breathing blankets. And that's all. Thanks for your attention. Muchas gracias. And
Thank you very much, David. Really, I think it was very clear, comprehensive talk, where you summarize the key points with details and also prepare for deeply understanding by each one of us. So you really made the full list of TBMs, details of the TBM, and all the items. Some more detailed, the part basic, some just for reading by ourselves, which is other important part in these courses. So it's now the time for questions. I have several, but I give the floor first to some of our people in the course. This good friend of mine is making me to make a lot of exercise. Please, go ahead.
Okay, thank you very much. Indeed, has been very illustrative for me as well. Just a couple of questions, maybe it's useful for everyone. When you talk about HCPV, okay, the helium cooled, and then the WC, water cooled, what is the main difference? What is the main advantage of using helium instead of water for the pebble bed?
yes, this is a very good question because, okay, the water-cooled lithium lead, the main advantage is that it uses technologies that are already available in fission reactors. This is the main important point for the WCLL. The WCLL was studied years ago in Europe, also in the US, and was discarded by several reasons. The main reason is safety, because the problem is that tritium retain, I would say it in that way, tritium retention by water is a critical aspect, okay? But since we were not able to produce, I would say in another way, more political, let's say that all the technology for the water is already available in the market, okay, for the fission reactors mainly. And for that reason, the European program decided to bring with us again the WCLL. This is the main reason. This is the main reason. The main difference with the HCPV is that the HCPV uses helium. The technology with helium is much more complex. To extract the amount of power of the fission reactor with helium is really, it has a really high cost in terms of electricity, so at the end, money. So for that reason, at the end, the plant efficiency is not so high. In both cases, the plant efficiency is estimated to be around 30%. And 30% maybe is not quite competitive. And for that reason, we are thinking in another kind of blankets, going to higher temperatures and so on to reach efficiency of 40, 45, 50%. But the main difference between helium and water is that pumping the helium is really difficult. And in addition, you have a lot of losses of helium in all the circuits. So at the end, it's a matter of money also.
But what is the advantage of helium instead of water? Only the tritium retention? Or?
No. The advantage of helium between versus water, helium is an inert gas. This is the first one. And this inert gas has to cool the first wall. The first wall is the first component that the neutrons see. So if you have water there impacting by a lot of neutrons, you have radiolysis, you have the water is also highly corrosive, you have corrosion products, you have all these things. With helium, it's an inert gas, you avoid all these problems. This is the main advantage.
Okay. Just the second question is for the demo reactor in the future. So you are saying, okay, we are going to try, there are two candidates for the driver breeder blanket, the HCPV and WCLL.
Excellent.
So, but only one of them will be installed, no?
Exactly.
So it will depend on the results from ITER, or?
Should be. But if you see the timeline, maybe you can go to the presentation of Angel, where you will see the timeline for ITER, for demo, and so on. The operation with the TVM will not finish before we start the final design of demo. This means that we will not have all the results of the TVMs for deciding if this is the most attractive or the best blanket to be installed. And this is a problem, of course. But in the meantime, of course, we will benefit of all the results that we will obtain. But the decision will be made in 2024, I guess, 2025, and will be based on other political aspects, I would say, as usual.
Yeah, because the time is not enough just to wait for the results. Yeah.
ITER will start the operation in 2027 around, and the decision for the driver blanket will take place on 2024. So this is the answer to your question.
Thank you very much. Any other question in this area? No? Okay, so then I can
it's
hear
late.
And ask you another question, David. You never thought in Flyby instead of lithium lead?
Yes, indeed. One of the advanced blanket which was considered this in these last 2 years. Consider this molten salt, but to be honest, the mature of this design is really low, and it's considered as a future option. But right now, for my understanding, no one in Europe is working on that.
Okay. My second question is one aspect that we were making research a long time ago was about the equation of state of lithium lead, the eutectic, the effect of the eutectic composition. Lithium lead that these guys use is 17% in lithium, 83% in lead. So my question is being, when you modify the composition of the eutectic, manufacturing, blah, blah, blah. Which is the fact, and how is the knowledge that you have about the consequence of that equation of state?
It's a quite good question. The first point is that if we modify this percentage, of course, we are going to modify the tritium breeding capability, not the tritium breeding capability. The capability is what it is. But our models will be modified, of course, because we calculate for this amount of lithium. So at the end, we are developing a blanket for a certain TBR with this amount of lithium. And if we finally, for manufacturing processes or whatever, we have a different amount of lithium, maybe the tritium that we are going to produce is not the same that we estimate at the beginning. This is the first point. Second point, and quite important, the properties of the liquid metal. Some properties depend on this lithium amount. For instance, the tritium solubility. Tritium solubility is quite important number because tritium solubility, a lot of processes depend on tritium solubility. Tritium permeation to the environment, tritium extraction, the ability that we have to extract the tritium from the liquid metal, and this is essential for the self-sufficiency, depends on the tritium solubility. And we have found several experiments where they modify a little bit the amount of lithium and the tritium solubility change completely. So to warrant this percentage of lead and lithium is essential for the good functioning of the reactor, of course.
Okay. Oh, Maria.
No, I have a problem. Boys.
No, this is for the screening.
Ah, okay. In relation with this, David, since lithium is the element which products the tritium, if it is being changed during neutron transmutation, then the solubility and all the properties of this lithium lead changes from the eutectic to the other compositions.
Exactly.
No?
And this is one of the main advantages of the concepts with the liquid metal. The liquid metal can be routed through a complete loop. So we are all the time refreshing the liquid metal inside the breeding blanket. So I have not shown
Really?
because I wanted to focus on the tritium extraction system and the heat exchanger, but of course we have other subsystems. One of them is the
supplier of lithium?
No me acuerdo el nombre. It's a component to assure the amount of lithium that we have in the system. It means that we are putting additional lithium in our alloy before entering again into the blanket. So all the time we have also to perform chemical analysis and so on. We have to maintain the chemical composition of the liquid metal all the time inside the blanket. And this is a quite important advantage because what Maria said is completely right. You are all the time impacting with the neutrons in the liquid metal, so we are losing lithium, so you are modifying even in a small percentage the eutectic composition, but thanks to this routing of the liquid metal, you are refreshing all the time with new liquid metal. In the case of the solid breeder, this also happened, but the solid breeder is inside the blanket all the time. So you cannot solve this problem.
I have a question. I also believe that dual coolant is a very good solution. But one question. In dual coolant, you have just one loop. So you have tritium extraction, power cycle.
Exactly.
That, from the point of view of regulatory, from the point of view of accident, from the point of view, could generate an additional problem,
So, one of the main advantages of the dual coolant is also that the main problem of the Dcll is that the liquid metal flows at high velocity. Okay, high velocity, high flow rate, and so on. But this is, on the other side, this is an advantage because flowing at high flow rate means that we have very low tritium concentration. And this low tritium concentration makes that the tritium, for the tritium is more difficult to permeate through the surface, because the permeation of tritium is driven by the difference of concentration between a plate, basically. Okay, so at the end we have low tritium concentration, so low tritium permeation. At the end, this could be a problem, but all the time I presume that we could be under the level. So this is not sure if this answers your question, but
yeah, perfectly. My last question. Any other question? My last question. Solid breathers. Solid breather, in my personal view, David, I want your opinion, is really problematic. I mean, when you want to extract the tritium, you need to extract the pellet, you need to break the pellet, because the tritium is inside the pellet or not?
No. Yeah, this is a good point. Maybe I didn't explain quite well. We have the pebble, okay? We have different pebbles of this size, and in between the pebbles there is some space. Right?
Okay.
It's not perfect, it's not a solid. Yeah. And we flow a purge gas, helium, and in this helium we don't have tritium, so the concentration is 0. So this difference in concentration between the pebble and the gas makes that the tritium diffuse through the pebble and goes to the gas, and we extract.
Now I understand.
Okay.
Now I understand.
Sure.
If I can add something to this, the pebbles are a solid material, but it has at least 15% of porosity. And that's why
right.
also the helium, the purge gas, also sweeps through the solid and extract the...
I got in my mind the model of this tetracarbon boron pebbles, which are really solid. I mean, there's no porosity at all. Inside, you put different components. For example, transmutation, actinides, or something like that. I was taking that concept. No, the concept is 15% of porosity, so flow 15. Yeah, okay.
So a last thing, because this was your last question, I guess.
Yes.
Okay, so I wanted to take this opportunity, because I see a lot of students here, and I prepared just 2 or 3 slides. It's quite rapid. This is just to say you that we have in CIEMAT, we have implemented the liquid metals laboratory, and this is quite interesting because I wanted to show you all the facilities that we have, and maybe it's interesting to you because maybe in future we will have grants or some. And just a few words. We have lead lithium loop to study corrosion. We have another corrosion for in static, okay, for a static experiment. We have lead lithium and we put the samples inside and wait for a certain time and we study corrosion. We have another experimental loop called Clipper, which is to study tritium extraction techniques from the liquid metal. We also perform some chemical analysis of the liquid metal. It is quite important. We study the melting point and the lithium concentration, the amount of impurities inside the liquid metal, and so on. We have designed also, this is for DONES, because we manage also in CIEMAT, in my group, we manage the activities for the liquid metals, both for the breathing blankets and also for DONES. LITEC, which is a prototype for the lithium loop for purification in DONES. We have also an experiment for tritium extraction from pure lithium, and this is also for DONES, LIDER experiment. And okay, this is a summary of all the experiments. We also perform permeation experiments and development of instrumentation and so on. So if you are interested, please contact, and maybe in future we will have some opportunities.
I am really happy that you present this, David. In fact, I don't know if I will give you my pardon.
Why?
Because before you didn't say nothing. Thank you very much. No, this is very important. This is very important. You see, these guys, they make a lot of things. So and you are young people that need to feel in the future these facilities.
Okay.
Thank you, David.